to try again. Share screen. Oh, I want to restart. No, I don't want to restart. Maybe that was part of the problem. Okay, can I get a thumbs up or a thumbs down to make sure that people can actually see what's going on?
I can see and hear you.
I can see.
I can see too and hear.
Oh, I cannot hear you yet. Okay, can somebody say something?
Oh, can you hear me now?
Okay, yeah, I can now. Okay, yeah.
Okay,
sorry.
we've been talking and I thought you could hear us.
No, so when my session crashed, I think it decided to also disable my headphone, but I just reset my headphone. So, okay, sorry about that. Okay, so let's go back to what we were trying to do. We're talking about binary strings, length n, no 1, 1 anywhere. Okay, so basically, if you have length 1, then they're exactly 2 strings, 0 and 1. Right, that's pretty easy. If length 2, so the answer is 2. Length 2, right, there's 0, 0, 0, 1, 1, 0, but 1, 1, of course, is not allowed, so there's 3. 3, there's 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1 doesn't count. Okay, I'll write 0, 1, 1 anyway and cross it out. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. These two don't count, so the answer is 5. Okay, and then you can try to do more and try to find a pattern. Obviously, you cannot do all 2 to the n strings and then count which one is okay and which one is not, because they're too much when n is big. So then the question is, how do you decide? How do you figure this out? So basically, if you have length n, and I don't know exactly how all of you came to the conclusion this is Fibonacci numbers, but if you have length n, you have n positions. And you can say, well, the last position can either be 0 or 1. Okay? If the last position is 0, then the previous n minus 1 characters can be anything as long as there are no ones, no 2 consecutive ones. So if the answer is f of n for length n, then the number of strings that ends with 0 and satisfying the required property, it's f of n minus 1. Because any strings of length n minus 1 that doesn't have 2 consecutive ones, you can always stick a 0 and you can get another string that works of length n. If you have a string that ends at 1, then the previous one is also fixed because it can never be 1, it must be 0. If the last character is 1, the second last character must be 0. And then basically the previous n minus 2 characters can be anything as long as there are no 2 consecutive ones. So the number of possible strings is exactly f of n minus 2. And since the strings that you're looking for length n either ends with a 0 or ends with a 1, there's no other choice, then this is the recurrence is basically this, right? And then of course it's a slightly modified version of Fibonacci numbers because the base case starts here instead of 1 and 1. But other than that, it's basically Fibonacci numbers. Okay, and then of course there's a problem that Fibonacci numbers grow too big, so you basically have to do percent or mod 10 to the 9 plus 7 at every step to make sure that you don't go too big. But that's a relatively minor step. Is that how you came up with this idea?
Yeah.
Anybody have a different way of getting this conclusion? Okay. Now this is a complete aside, but that is still kind of useful sometimes. I don't know about I might have said this once quite a while ago, but let's see if I did or not. So let's say that you want to compute Fibonacci number, like f of n equals to f of n minus 1 plus f of n minus 2. And let's just say that you want to compute things mod m. M would be this 10 to the 9 plus 7 or any other thing. Doesn't matter. So it doesn't overflow. That's the only important thing. It doesn't overflow. What if I want to compute f of 100? How would I do that? What kind of structure, control structure would you use to write this if you were to write code? Would you use a for loop, a while loop, recursion?
I first did my program using recursion, but then I did like 1 through 5, and then it was good, and then I did like 65, and then it just froze because it was taking too long.
Yeah.
So I had to switch to,
yeah. So why does it take too long if you use recursion?
because it's calculating the same numbers over again.
Okay. So if you use recursion, you can avoid that problem by using basically switching to dynamic programming. So you have a table in the answer, right? Let's say, I don't know, 101 like this, and initially maybe set them all to 0, and then in your recursive function you would say something like this. You do the standard thing. If n is 0 or n is 1, return 1. Otherwise, return f of n minus 1 plus f of n minus 2 kind of thing, right? Now, why do I write some space here? Because what I'm going to do is I'm going to say answer n. So I'm going to return, but I'm also going to store this answer. So, and the first thing that I do when I enter this is if answer n is bigger than 0, that means I've already computed it. Then I just return. So I don't recurse if I've already seen it. Okay, so if you do this, then this will be very fast because every single entry can only be computed once. And as soon as you computed it once recursively, or whatever way you do it, this is now stored in the table. And if anybody asks you the same question again, you will not keep going. You will just return the answer. Does that make sense?
Yep.
Okay, so if you do this, it's linear time, big O of n. Okay, because every entry can be computed once. Now, you can also do it the other way. You can do it as sort of the for loop. Sometimes it's called bottom-up dynamic programming. It's a top-down, but you can also do something like this. Oh, I forgot. Wait, I forgot the mod m. Okay, so this is the for loop way, and again, this one is really clear that this is big O of n because this loop runs n times. Yes. Are we all agreeing? This is This is all child's play. Okay, so now imagine I asked you to compute f of 1 billion. Okay. So f of 1 billion. If you use either of these approach, what is going to happen is that it's going to take 1 billion steps, which is too slow. Now, I don't remember if I have ever told you how to compute f of 1 billion quickly. Have I? Anybody remember if I have?
I don't think so.
Okay, I might not have.
Do you
Yes?
use the like Fibonacci formula with the matrices and stuff?
Maybe.
I heard
What
about
is,
that when I was
you heard
searching it
about
up.
that? Okay. Oh, shit. It's this, okay, hang on. This whiteboard app is kind of very flaky, but it's, when it works, it's the best one that I can find on Linux. But anyway, okay, so the matrix thing. What is the matrix thing? Now, the Fibonacci formula. Do you?
I don't remember it. I just remember that it was a thing.
So you can look it up, I suppose. And, well, we'll just click on the first link because that's all we do. And where's the formula? Okay, there's a lot of stuff going on. The formula at the end is, here it is. This is the formula for Fibonacci numbers. Well, it's horrible. Why is it horrible? Because you've got square root of 5s, which is floating point numbers. Even though when you compute everything, it's supposed to cancel nicely into integers. When you actually try to use floating point numbers, probably not going to cancel it properly, and you'll get all sorts of strange things. Plus, we are doing mod. Okay, but if you actually read the derivation of everything, if you all the way go back to all the way to the beginning, it turns out that this is actually what you need. So let me just try to write this. Let me write this here. So if I have Fibonacci number f of 0 and f of 1, okay, this we know is 0 and 1, and it's 1 and 1, or whatever you decide your base case to be. I'm going to write it as a vector like this. Okay. And I'm going to hit it on the left with a matrix that looks like this. Okay, so what is it going to look like? Well, if I do matrix product, 0 times F0 is nothing, 1 times F1 is F1. And then here it's just F0 plus F1, right? Which of course you know that F0 plus F1 is just F2. Okay, are we okay so far?
Yep.
What if we hit this matrix, hit this vector with the matrix square? Well, we know that when I multiply by one of them is F1, F2. So F1, F2, and hit it with this matrix again. And by the similar argument, you will see that it's F2, F3. And if you do a few more steps, it should not be hard to convince yourself that if I do 0, 1, 1 raised to the nth power, that's exactly f of n plus 1. Okay? So what are we going to do? We're going to raise this matrix to the nth power. How do you do that? Well, we'll talk about that later. And once we have a matrix, a 2 by 2 matrix, then you can multiply by this vector. Actually, you don't even need to get both of these because you only need this one. And then you'll get the answer. So you only need to compute the matrix exponent, the matrix power. Then you say this one times this one plus this one times this one, and that will give you this one. Does that make sense?
Yep.
Okay. Now, how do you compute a matrix power? And you might say, well, it's not actually any easier, right? So I have this matrix, 0, 1, 1, 1, call it A, and I want to compute a to the power n is what? Well, a to the power n mod m, right? So we do things to overflow, so we'll do everything mod m. But anyway, how do you compute a to the n? Well, you take a matrix, you multiply by itself, and you multiply it by itself, and you do it n times, right? That's how you exponentiate things n times, and you say, well, how is that any better? Because you're multiplying n times. When we talked about n was a billion. And if you do it this way, then it's going to be too slow because I'm still going to multiply something a billion times. So how do I compute a to the n quickly? I think this I have told you before. A to the, I don't know, doesn't really matter what it is. Let's just make up a number, 71. So the process is always the same. You look at the exponent, and if the exponent is odd, then you say a times a to the 70. Okay, so that's not very exciting, right? A times a 70, everybody can do that. But now you're going to recursively compute a to the 70. And this time the exponent is even. When it's even, I can divide like this. So I recursively ask, what is a to the 35? And then in one extra multiplication, I manage to double it to 70. Okay, now 35 again, it's odd, so I'm just going to write only a 35 here. It's a times a to the 34. And then when you compare a to the 34 again, you can say this is a to the 17 squared. So recursively you compute a to the 17, and then in one more multiplication, you get to a to the 34. So basically, whenever you see an even number, you can halve the exponent. If you see an odd number, you can drop it by 1, and dropping it by 1 will guarantee that the remaining part is even, which you can then drop by half. And so more or less, you can say that every 2 steps, you're guaranteed to drop the exponent by half, at least, possibly more. And so the number of steps you need to drop it down to a to the 1, it's basically log 2 of 71 times 2. So this is what is called a fast exponentiation algorithm. And if you want to compute a to the n, a can be matrix, can be numbers, doesn't really matter, as long as it's normal multiplication, any kind of multiplication to form the exponents. You can compute this in big O of log n steps. So when we look at n being a billion is actually about 2 to the 30. So that's basically about 60 steps, because we said that in 2 steps we can reduce it by 2 steps by half. So this is something that you may or may not have seen before, fast exponentiation. Sometimes, depending on who teaches 3620, they would talk about the fast exponentiation. I don't know if you saw that last term. But
Yeah, we saw it a bit.
yeah, so that's how you would do it. That's how you would do it. Compute Fibonacci numbers very far into the sequence quickly. All right, that was a big aside. I don't know if do I even need to show you the code for this. I mean, this is basically it. There's not much to do. The only thing I would say is, because the answers is always the Fibonacci numbers, so I actually compute them all at the beginning instead of computing for every curve. So I compute them all at the beginning, and then every curve I just look it up. I don't have to compute them again. That's the only minor optimization. Okay. Any questions? Now, I think election is another one that some of you tried. Luke and Jenna, I talked to Jenna quite a bit about this problem. Did you ever get a chance to try to fix it, Jenna?
No, I was working on schoolwork this week. I didn't get around to it. I
Okay.
kind of have an idea how to do it, I think, but
Okay, no problem. Okay, so let's quickly go over what the problem is about. So there are n people that are voting for two candidates. Everybody votes for one of these two candidates. So if you want to win, a candidate needs to have more than half the votes. And at some point, you have counted a certain number of ballots, M. You've got V1 votes for candidate 1 and V2 votes for candidate 2. So, you know, when you're election night or whatever, they will start counting, and at some point, they will count 10% of vote, and they say, we now announce that candidate 1 has won the election. And then you say, well, what the heck? The only 10% of votes have been counted. How can you say that? So this is kind of a problem on that. So now, if you assume that the uncounted vote, each of the remaining votes, has a 50-50 chance to go to either candidate. Okay, so in real life, you might have a different percentage, but for this problem, we're going to assume that every vote has 50-50 chance of going to the two candidates. That makes you think that you can announce the win before all the votes are counted. So if the probability of winning strictly exceeds a certain threshold W, the victory is yours, but we better be sure of this. So you have 100 up to 100 cases. Then each of the cases has N, which is the number of voters, and in this case, up to 50 voters. V1 and V2 are the votes that have been counted for each candidate so far, and the sum is always going to be less than or equal to the total number of votes, but it could be less. And then W is how certain do you want to be before you announce a winner? Do you want to be 80% sure or whatever it is? And then it says if the probability that your candidate will win is strictly greater than W, print this. If your candidate has no chance of winning, print recounts, otherwise print patience. Okay, so there's sort of the mathematical side, and then there's the implementation side of this problem. So let's talk about this. So you have N voters. You have V1 and V2 votes so far. And then you have, let's call it R equals to N minus V1 minus V2 remaining votes uncounted. And these votes are 50-50 for each candidate, okay? So you have to kind of flip a coin, I suppose. So the question is, what's the chance of the probability that candidate 1 wins the election? Okay, so how do you win the election, i.e. more than N over 2 votes, more than half the vote? And when I write this, you have to always remember that N is an integer, so when you N divide by 2, I'm writing N over 2 like this as opposed to N/2, because this one is the C++ version of division, which may or may not be what you want. Because it's integer division, I'm writing the mathematical N over 2 so that this one can have fractions. Okay, so anyway, what are some edge cases, right? It could be that V1 it's already greater than N over 2. So whatever you count, it's already majority, so you are going to have 100% win. That's it. You already won. It could be that V2 is already greater than N over 2, in which case there's nothing you can do. It's 0%. Those are the sort of two edge cases. But then there's sort of anything in between. Maybe neither one have completely won yet. So what to do? So what you have to do is you have to say, well, what is the chance or what is the probability of candidate 1 getting, let's just say, V votes, whatever V is. And V is at least greater than V1. Okay, because he already have V1 votes, so what's the chance? If we can figure it out, then maybe we can answer the overall question. So whatever V is, what's the chance that he's going to get exactly V votes? Exactly. Okay, so you already have V1 votes. Want to get V minus V1 more votes, right? Remaining, it's N minus V1 minus V2 votes. So remaining, so there are votes left. Okay, each one of them can be candidate 1 or candidate 2, right? You don't know which one. Each one has a 50-50 chance, and you want exactly V minus V1 once. So what we're talking about is you have R slots, R people, R remaining votes, and you want to know how many ways there are that have exactly this many ones. And it's the binomial coefficient. So that this many ways for the R remaining votes to have exactly this many ones. Does that make sense? If that makes sense, what's the probability that this happens? Well, if there are this many ways that has exactly this many ones, and how many possible votes distributions can there be? 2 to the R. So the probability of getting exactly this many ones, this many votes for candidate 1 is this binomial coefficient divided by 2 to the R. Does that make sense?
Yep.
Okay. So this is if we want to get exactly V votes. So I want candidate 1 to get exactly V total votes. Then I would use this to compute my probability. But in order to win, V can be anything from N over 2. So this time I have to, V can be anything from N over 2 plus 1. So this is, now I'm writing the /1 because N/2 plus 1 is the smallest number that is at least that is more than half of the total. N over 2 plus 2 dot dot dot, and then I guess N minus V2. That's the most you can possibly have, because whatever V2 already has, you cannot get them. So you have to basically use this formula to compute the probability of getting exactly this many votes, all the way to this many votes, and sum them all up, because those are all the possible cases of candidate 1 winning. Okay, and so what you have to do is you have to add up all this probability and ask if the total probability is greater than or equal to the W that they tell you, the probability, how sure you want to be, then you say we won. Otherwise, you don't, you say the other thing. Okay, that's part of, well, that's the mathematical part. Are there any questions about the mathematical part before I talk about the implementation side?
No, I think I got the math part. I think I was just doing something wrong in the implementation.
Okay, all right. So did you do more or less what Jana did? I don't know
Yeah.
if you saw her code.
Yeah,
Okay,
no, we were
well,
doing pretty
okay.
much.
I know exactly what was wrong because I fixed the code and get it accepted. So the first part is, how do you compute these binomial coefficients? Okay, so generally speaking, when you use binomial coefficient, there are many ways you can compute it. But the problem is these numbers can get big, especially the top part is up to 50. Well, it turns out that choosing up to 50, a binomial coefficient n choose k, I guess I use n choose k like this, it's always less than equal to 2 to the n. It's a very rough estimate because one of the things that you may remember, if you add up all the binomial coefficients of different k, that's exactly 2 to the n. So if you pick any one of these binomial coefficients, it's guaranteed to be less than equal to 2 to the n. So what am I trying to say? If n is at most 50, then this is at most 2 to the 50. All your binomial coefficients are going to fit in a 64-bit integer. Okay. So how do you compute binomial coefficients, especially when everything fits? The best way to do it is Pascal triangle, because you don't have to worry about division, you don't have to worry about overflow. So Pascal triangle basically says, so you have a long 64-bit integer binomial, and then you have some limits up to 51, 51, and then you do something like this at the beginning for n equals to 0 and let's say to the 50. I'm not sure why I'm writing this one. I just show you the code, but anyway, then you say binom n choose 0 and n choose n are both 1, and then you subdue the interior of this Pascal triangle. Binom n choose k is binom n minus 1 choose k plus binom n minus 1 k minus 1. Okay, so you run this loop, this double nested loop, and it takes basically 50 square iterations, roughly 51 square. And after that, all the binomial coefficients are computed. You can just look this up. Okay, so that's the first part. The second part, so of course, remember that we're using long. We're not using doubles because we don't want to lose any precision if we can avoid it. And in here, we can definitely avoid it because all the numbers are going to fit in 2 to the 50. So now the next thing is you add up all these probabilities. So your probabilities are basically a bunch of binomial coefficients. I'll just write it like this, a bunch of binomial coefficients. And then all divide by 2 to the r. And then you're going to compare it, I'll put a question mark here, against w. And now you're going to divide by 2 to the r, which may or may not be great because now you have fractions again, or decimals. But you don't have to divide by r to do this check because you can just clear the denominator and do this check instead. That's equivalent. And now if you do this, the check this way, this is integer, this is integer, there's no rounding error of any kind, and you're never going to have to worry about whether your answer is correct because of rounding error. Remember, whenever you compare things here, when I write things like this, you always have the possibility of equal, right? And if you have round off errors, it's almost impossible to get this thing right, to get the equality right. So if you can avoid round-off errors, then you should. And in this case, you can. So that's the other part. Now, it turns out that this divide by 2 to the r is actually completely safe. You can actually do the division, get the floating point, and you'll never get a round-off error, because the way that floating point numbers are represented in computers, multiplying and dividing by powers of 2s will not introduce any rounding error. But I still think that it's good practice to think about this, and if possible, just avoid going to doubles or whatever it is. Okay, so that's the part where I think Jana, I haven't seen the code from Luke, but that's what happened with Jana's code. And I'll just show you my solution. Okay, so main is here. So this is exactly what I did, what I showed you. I compute all the binomial coefficients to start. And then for each case, how do I do it? I read in N, V1, V2, W, and all that stuff. The remaining number of votes is N minus V1 minus V2. And then for all the remaining votes, basically, I guess R is the number of votes that goes to candidate 1. If the V1 vote plus R is bigger than N over 2, then I add up the binomial coefficient. So if the total number of votes is enough to push V1 over the half line, then I send it to add the binomial coefficient. If there's no way, then I lost already. Otherwise, this is where I do this. Why do I multiply by 100? Because W is in percentage. So that's why I multiply by 100. But otherwise, this is what I told you about. This is for the left shift operator. So when I left shift a certain number of positions, that's equivalent to multiplying by 2 to the RAM. It's like if you're adding zeros to decimal numbers, if you add 2 zeros, that means you're multiplying by 100. So in binary, if you add 2 zeros, you're multiplying by 2 to the 2. So that's the main part of this code. Okay, any questions? Does it make sense, Luke and Jana, since you tried this before?
Yeah.
Yeah, I just got accepted. That's a lot easier than it would have. I would have made it anyways.
Well, I mean, your math is right? It's the implementation.
Yeah.
So, okay, so now let's recap what have we done in the first 2 problems. The first problem was counting that somehow you turn it into Fibonacci numbers. Here you count and somehow you turn it into binomial coefficients. But if you think about things here, even when you do the binomial coefficients, one of the better ways of computing these things is a recursion or some kind of recursion. And with counting, probability, and so on, some kind of recursive or dynamic programming type of thinking is usually the way to go. I can't say that it's always the way to go, but usually that's the easiest way to count. And we'll see that again in some of the problems later. But that's one thing that when you're asked to count something, if it's not something obvious what the answer is, you should think about, can you break it down into smaller problem and recurse? Because that's a very common technique that works when you do combinatorics. And if you actually, I think, is it true that some of you are thinking about taking the combinatorics course coming up in the fall?
I'm taking geometry instead.
Oh, okay. Okay.
I am also taking geometry.
Okay. Well, anyway, if you do take combinatorics, recursive thinking is a very common technique that's used to solve all sort of stuff. Okay, so let me go to the next problem. Now, the next problem that people tried here, Luke, you try E. should we, no, actually, let me go to C first. C is, the easiest problem in the set is actually C. And then D and E are harder. So I'll talk about C and then I'll jump to E. And then
I think we both actually tried C and D. We just didn't submit them.
oh, did you
'cause
get it? Oh, do
I
you
knew
know
I
what to do?
didn't. Well, I knew I didn't have the right answer. That's why I didn't submit it.
Okay. All right. So let's okay. So maybe you didn't understand what C is about because C is actually the easiest problem of the set. Okay. So let's read this. Spies use attributes to disguise themselves to make sure they're not recognized. For example, when putting sunglasses, a spy suddenly looks completely different and cannot be recognized anymore. Every combination of attributes gives a different appearance, but not all combinations are possible. For example, a hat and the turban are both headgear and cannot be used at the same time. Given the list of available attributes, compute how many distinct disguises can be made. So you're given one positive number, which is the number of test cases. Per test case, you're given n, which is the number of available attributes. For each attribute, you have the name of the attribute and what category they belong to. Everything is up to 20 letters. Everything, all the names are distinct. For a test case, one line with an integer, the number of possible distinct disguises that can be made with the given attributes, such that at most one attribute from each category is used. So let's try to figure out how to get these answers, 5 and 3. So here you have a hat, that's a headgear. You have sunglasses, which is eyewear, and you have turban, which is headgear. So what's going on here? You basically have headgear and eyewear. Headgear, you have 2 possibilities. Eyewear, you have 1 possibility. So how many choices can you put for headgear? 3, because you can choose to do nothing as well. So you can choose the hat, you can choose the turban, or you can choose to have no headgear. How many eyewear can you choose? You can choose to have sunglasses. You can choose to have no sunglasses. So altogether, the total number of possible configurations is 6. Which headgear you wear or not, which eyewear you wear or not, the total possible configuration is 6. So why is the answer 5? Because one of the configuration includes not wearing headgear and not wearing eyewear. And that is no disguise. So whatever answer you computed here, you have to subtract 1 from it. And that's the answer. Over here, you only have 1 type, face, something for the face. So there are 3 choices, and then altogether there'll be 4 choices because you can decide not to wear any. But then, of course, not wearing any, it means you have no disguise, so you have to take that answer -1, which is what gives you 3. Okay, does that make sense?
Yeah.
Were you thinking about this at all, or were you thinking about something else?
I think I was making it a lot more complicated in my head. And I didn't think of
Okay.
that.
So if that's, I guess if that's, you understand this and you agree with this, the code is actually relatively straightforward. Okay, so the main doesn't really have much to do, just read in the number of cases and call solve that many times. So everything happens in solve. So what is solve? I count how many times each category appears. So do I have 5 headwears? Do I have whatever it is? Okay, so what to do? I read in the number of things. For each thing, I read in the name, I read in the category. I actually don't even care about the name. And then I just say I have seen another thing in that category. That's all I'm doing. Then the answer is basically the product of all the category counts plus 1. So if I have a category that has 5 things, that means I have 6 choices. Each of the 5 things or not using it. And I'm just looping through all the different ones. And so I guess I don't know if you've seen this. This is a C++11, sorry, C++17 feature. It's relatively new. basically I'm looping over the map. All the elements are pairs of string, the key and the value. So this allows me to not only loop through the elements or the pairs, it also automatically takes them apart. And in here, I actually don't care about the category. I just care about the count. So then I just multiply by f+1. And then at the end, all I'm doing is take the answer and -1 for the case where I basically decide to choose to not use any disguise in all categories. That's the answer. Maybe you didn't quite get what the problem was asking. I don't know. If you understood what the problem is asking and know how to count that, it shouldn't be too bad. Maybe the sample input and output was not too helpful because they're too easy. Anyway, that's this one. You guys have any comment you want to tell me?
I think I knew what it was asking. I just made the math a lot more complicated than it needed to be. Because I was thinking more like, you count each one on their own because you can use each one on their own. Okay, so maybe I didn't know what it was asking because I wasn't thinking like you can't use one.
Uh-huh.
I was implementing that, like that you could use one on its own or whatever, but you're kind of thinking the other way that you could not use something.
So just worry about, okay, if I use this one, then I can't use the other one, headgear, and you have to try to figure out how to discount that somehow.
Yeah, and that
Otherwise-
made it a lot more complicated of an algorithm to do it that way.
Yeah. Yeah, that's all I'm gonna say. Makes it a lot harder. I can kind of see how I can turn it into a very complicated dynamic programming that remembers which category you have already used or not. But in fact, if you just group all the category one thing, consider them on one chunk and choose one, and then move on to the next category and so on, that makes it a lot easier, right?
Yeah, for
Anyway.
sure.
Yeah. Okay. Okay, so that was meant to be the easiest one. Maybe I should have put it in first problem, but I guess the first one was not that hard either once you figure it out. All right, the last two are significantly harder, although maybe with this coalition problem, there's a lot of reading, but well, if I show you the solution, maybe it's not so bad. So maybe I'll put Luke on the spot since you tried it twice. What did you try, and what was the verdict when you submitted it?
The verdict was I passed one case and then I failed the next case just as a wrong answer. I'm wondering if because I used doubles again, that could have, like, maybe I should have used integers somehow the whole time.
In this problem, I don't think it's a problem.
Okay.
Because the numbers that they give you, okay, these are integers though, but I don't think it's a big problem because you are allowed to have some tolerance in your answer. You're allowed to be a bit off.
Okay.
Up to 6 decimal places, it has to be correct, basically.
Okay.
So you're allowed to be a little bit wrong, but of course you're not allowed to be very wrong.
Right.
So do you want to tell us what is your
yes.
approach?
So I put everything in a pair and then I sorted that in decreasing order. So the greatest at the beginning. I think that's what I did. And then
decrease? So okay, your pairs consist of two things.
yeah,
The size of the party, SI, and then this probability PI, yes?
yeah.
Okay. So when you say you sort, which component, what are you sorting by? Are you sorting by the size or the probability?
At first I did it by size, so whoever had the most seats would be at the first. And then I made a special case in the sort that if they were equal to each other, then sort by the second. So like sort by the probability. So you want the
Okay.
greater probability first, but it goes by seats primarily.
Okay, and then what do you do?
And then I go into a for loop. So I go through that whole array and then I make a temporary pair. And that's equal to the first, that's just equal to wherever your array is at that position in I. And then if the seats is greater than, so if, yeah, your temporary thing is greater than like half the seats. So I said, like if it's greater than 75, then push that into the, like a results array. And then if not that, then go through the rest of the array and then add the first element. So add the seats and then multiply the probabilities. So I make a coalition kind of thing. And once that coalition is greater than 75, I put that into my result. And then I just keep doing that until I get all the coalitions. Then I sort the coalitions by probability. And then I just,
Do you get
see.
all the, are you sure that you want to always have the largest one first?
You want the largest probability first.
Yeah, you want the largest probability, but
Yeah,
when
yeah.
you
So I
con-
did a different sort function that sorts by probability. That's in my
right,
results array.
but when you consider all the parties, then
Yeah,
add them together. You had it sorted from the largest party to the smallest party first.
at first, yeah.
Yeah, so are you sure that's the right thing to look at?
I'm starting to think maybe I should have sorted it by probability maybe to start. Because I did probability in my results, but then in the first part I did it by seats.
Well, okay. So, if you have let's say that you have a very large party, but it has a very low probability. That's
Right,
probably not something you want to look at.
right.
But at the same time, if you sort it the other way, you can have the same problem. You can have a very large probability, but a one-person party which hardly
Yeah.
contributes to anything.
Yeah. So what I was
So-
trying to do in my algorithm is pretty much get any coalition that was. Oh, I see. Yeah, I think yeah, okay, never mind.
Okay. So let me just make sure, because I don't know if everybody read the problem. Let me just make sure that I kind of quickly summarize what the situation is. You have a bunch of political parties. Let's just say it's up to 150. Each party has the number of seats that they have won, called SI, and a probability that's between, let's say, between 0 and 100. It's a percentage, okay? And we won't worry about what the probability means. You want to find a combination. Oh, sorry, maybe I should say, should I use the word combination? Sure. Or maybe a subset. Subsets of parties such that the total seats of all the parties that you chose, it's at least 75. 75 or 76, I can't remember. It's not a huge
Yeah, I think you need
it's
76.
Okay, it's a minor detail that we can easily fix, but might as well get it right. So at least 76, and the product of all the probabilities of the subset, it's maximized. Okay, so that's the thing. So if we look at this example here, if you choose these two, you got 90 people, 90 seats together, and it's 60% times 90%, which gives you the 54%. okay? Or you can try, if you try to put these two together, it's 56%, but it's not enough because 35 plus 25 is only 60 people. And then if you try to put 35, this one, and this one, and this one together, then these three parties together is enough. But then 0.8 times 0.7 times 0.9, it's smaller than 54. That's kind of the idea of this problem. Okay, you want to find a bunch of things, find a bunch of parties, put them together so that the size, the total size is at least 76, and the product of the probability that you chose, it's maximized. Now, here's my question. I think if I remember correctly, all of you took 3620 last term, yes? So if I'm correct,
Not me yet.
oh, so okay, so
I'm
you're excused.
on 2720. currently.
Okay, so you're excused if you don't know the answer, but I will have to buck the other two. So does this look like any problem that you have seen in 3620 last term? Is there anything from 3620 last term that you got reminded of when you read this problem? Okay, it's not the most obvious thing to look at, but you have 150 seats total, yes? And each party has SI seats and PI probability, and you want to find some subsets of parties with maximum probability product. Okay. Let's pretend that we're not trying to find a maximum probability, the product of all the maximum probability. Let's imagine that I asked you a slightly different problem. I want you to maximize the sum of probabilities. Okay, this is not the same problem, but let's imagine that we're doing this. So what is going on here? If you imagine that this total seats, it's a knapsack of capacity 150, and each of these parties an item that has weight this much and value this much. You're trying to find out which item you should pack into your knapsack to maximize the total value, given that you have a certain capacity. Does that make sense? Do you remember this knapsack problem?
Yeah.
Right, so knapsack, you have some capacity C, and then each item has some weight and value. And you're trying to make sure that the chosen items, the weight, the total weight, it's going to fit in this capacity. And then you want to maximize the sum of the values that you chose. Now, why do I bring this up? Because when you actually look at the dynamic programming solution for knapsack problem, you don't just compute the best possible answer to hit exactly this capacity. You actually compute the best possible answer for assuming the capacity is 1, 2, 3, 4, 5, all the way up to C. And so in this particular case, you're going to look at all possible ways, the best possible ways to have a bunch of parties to sum up to exactly 1 seat, 2 seats, 3 seats, 4 seats, 5 seats, all the way up to 150. And then you're going to look for basically the best answer out of 76 seats, 77, 78, 79, all the way to 150. So that's the first part why this is like knapsack. Does that make sense?
Yeah.
But there's a problem, right? What is the problem? The problem is I kind of just cheat, right? I told you that knapsack, you're trying to find the best sum of the values, but this is not knapsack, yeah? Because the problem asks you to find the best product, yeah? So what to do? What to do? How can we cheat? So I want to maximize product, but I don't know how to do that. What I know how to do is to maximize the sum. So what do I do? This is a sneaky, very sneaky trick if you want to do it this way. So I want to be able to maximize some product. Let's just say P1 times P2 times P3 or whatever. Okay, it doesn't really matter. Let's just say I have three things that I'm multiplying. I don't know how to do that. I only know how to maximize sum. So how do I make use of an algorithm that does something with sums to solve a problem that has to do with products? Okay, so the sneaky thing is I take the probabilities, Pi, and I change them to be the logarithm of Pi. Okay? And you say, well, what's going on here? Why do I take the logarithm? Because what I'm going to do now is I'm going to compute the maximum sum, which might, using the knapsack algorithm, maybe I find that the maximum, maybe it's this one, P4. Maybe I use these three parties and I sum it up. But now you remember that when you have log of sums of logs, that's the same thing as log of the product. So when you maximize the sums of the logs, you're also maximizing the log of the product. So whatever value you get after you maximize it, how do you change it back to the product? Well, this is your answer. Well, you can change back to the product by taking e to the answer. That will give you the product that you want. So what the heck did we just talk about? Basically, we're taking the product, the product into sum by taking logarithms. And if you want to go back, you take exponentials. So we take the original problem and turn all the probabilities to be the log of that number. Then solve the knapsack problem the way that we know how to solve with dynamic programming. And whatever answer we get as the best possible answer, we exponentiate that answer to get back the original probability that we're looking for. Okay, is that very convoluted?
That's pretty sneaky.
It's a pretty common trick when you try to kind of pass between products and sums. Like sometimes you know how to do something with sums. Usually sums are easier than product, but you want to do something with product. So it may be possible, in this case it is, to just take log of everything. And then you solve the problem for sum, and then whatever answer you get, you exponentiate and get the answer back. Or you can just completely ignore what I just told you, because maximizing product and maximizing sums are really the same thing. It will work anyway. So actually, what I did was I actually just used the normal knapsack algorithm, and every time I add the values of the items, instead I multiply. So I guess what I showed you was sort of mathematical justification of how this can be made to work, but here we are. So I read in for each item or for each party, I read in the size, I read in the probability, but probability of percentages, so I divide by 100. And then this is basically the setup for a knapsack. The first dimension is how many parties or how many items I've considered so far, and this is how big of the coalition or the capacity I've used. So 0, 0, if I have no item considered and I don't use anything, then probability is 1, because that's the empty set. If I consider first item and exactly that size, that much is used, probability is whatever they told me. Then I just go through each more party. I go through each possibility, each capacity. Then basically, if I can do, if I can use one fewer, if I can use one fewer item and form that sum, then I can decide basically not to use this item, not to use the new party, or I can use the new party. Basically, those are the two choices. If I don't use the new party, then it doesn't change the J. Otherwise, I have to change the J by adding the size of the new party that I include, and then the value is just whatever I used to have as the best one times the probability. Anyway, this is basically the knapsack algorithm. So if you don't know that very well, then I guess you can review that. And then finally, at the end, I just ask for all the capacity between 76 to 150. So all the different ways you can form a coalition that's bigger than half. What is the best probability out of all those choices? So anyway, this is the basically the knapsack thing. I could have, if I wanted to. So I said I can make everything log, and then I would just instead here. So I guess if I use log, then this has to be 0, because log of 1 is 0. Then I can, but then I have to be a bit careful, because I don't want the -1, I want something much smaller. What do I want to do? -1, something really big. And then if and then here I just add, and then here I would do I need to, what do I need to do? I need to exponentiate back. So let's see if I haven't screwed up, which is actually entirely possible. It should still work. So power log was not declared. Oh, aha! I did not include CMath. This was done a while ago when I didn't just include everything. That would be the reason. Let's see if this works. Wrong answer. Okay. Well, I guess it didn't work. I probably did something stupid somewhere. Anyway, okay, I'm not going to try to debug now. Anyway, so here it is. All right, that's how we do this one. Okay, just a minute. Let me go and see if I can mute the talk here. Okay, where am I? Okay, dice betting, I think is the last one. Okay, so, oh, before I go on, did the explanation for the last problem make sense, Luke?
Yeah, it did. I'll review knapsack a bit and try to resubmit that one.
Yeah, so knapsack is definitely something that if you want to do competitive programming, definitely something that you should know very well inside and out, because it's the basis of so many things, and it's certainly something very classic that people expect you to know. Okay, let's see here. Last one is dice betting. So this one, let's see here, they have a huge collection of 6-sided, 12-sided, 20-sided dice. Blah, blah, blah. He came out with a new game. He rolls this S-sided die n times and wins if at least k different numbers appear in the n throws. This S-sided die contains S distinct numbers 1 through S on the side. Since it's the only game only for one person, Gunnar and his friends decided to make it more fun by letting other people bet on a particular game. Before you bet on a particular game, you'd like to know how probable it is to throw at least k different numbers in n throws with an S-sided die. Assume that all numbers have the same probability of being thrown. Okay, so you're given n. Okay, so you're going to throw a die n times up to 10,000. K is the number of times, the number of different numbers you want to see, at least, up to 500. And S is the number of sides of the die, which is also up to 500. I'll put one line with the probability that a player throws at least k different numbers with n throws with an S-sided die. Okay. So this is pretty involved here. We have to make sure we know all the different parameters. So with n, which is up to 10,000, is the number of throws. S, which is then up to 500, is the number of sides of the die. And K, which is less than S, is the number of different sides showing up. Right. So if you throw it 10 times and it's always shows 1, then K is only 1. Okay, and they ask the probability that at least, is it at least? Okay, yeah, exactly. Let me just check. At least, okay. At least. At least k different sides show up in the n throws. Okay, so that's the question. What to do? What to do? So if n, it's small. I don't know, if n is like 3. Okay, so let's just make it really small. How would you do it? Well, you have three possible throws. Each one can be 1 through s. So you can generate all possible throws by saying s cubed. Right? Each entry has s choices. There are 3 possible throws, so you can try all possible s cubed choices and then check how many of them have k different sides. And then you just count and divide by s cubed, you're done. And in general, if you have n spots, you'll be looking at s to the n possible strings, the possible results that you count and check. But of course, n being 10,000 means that this is impossible. Okay, s cubed is pretty much, n equals 3 is pretty much the most you can handle with this approach. You can't do much more than that. So what should we do? Right, so of course, the total number of throws is s to the n. That's the total possible, total configurations you can see. And then you want to figure out of all those things, how many have at least k difference. How many have at least k different faces, different sides? Okay. Now, whenever you see the words like at least, it's actually harder to do, because at least k means it can be k, it can be k plus 1, k plus 2, and so on up to s. So sometimes it's actually easier to not ask at least, but exactly k. Okay. And then if you can answer that, then you basically ask the same question with different values of k. Right? K plus 1, k plus 2, and then you sum them all up. So we're going to change the problem into saying, in how many ways can you throw n times and have exactly k different sides showing up? So, number of ways in n throws to see exactly k different sides. And we'll call this f of n comma k. Okay? So you tell me n, you tell me k, and this function will give you the number of ways. All right, some of the simple examples, right? You always look for the simple cases. If k is, edge cases. If k is greater than n, okay, so if you have 10 throws and you want to see 30 different faces, the answer is 0. There's no way you can do it. Okay, you cannot see more different sides than the number of throws. Similarly, if k is greater than s, it's also 0. Okay, because there's not that many faces. Okay, those are the simple cases. If n is 1, well, if you only have 1 throw, well then k must be 1 as well. And of course, how many ways can you do it? S, not 1, because k, it's how many different faces you can see. you can, one throw, you can see any one of the S faces. And it all means that you, out of the one throw, you see exactly one face. Okay, so those are some of the base cases, edge cases. What about the general case? I don't know if that's all the edge cases, but let's think about the general case. So again, the best way to think about this is recursively. I have n throws. N throws. And I'm going to see what's going to happen with my last throw. Okay. I want to get exactly k distinct different sides in the n throws. And I'm going to look at the very last throw. What can I get? This last throw, I can either get a new face, the new sides, get a new side, or repeat a side that I have already seen. Those are my two choices. There are no other choices. Does that make sense? So if I get a new side, then what that means is that the previous n minus 1 throw, I must have exactly k minus 1 side. Okay, because I need to, if I get a new side, then the previous n minus 1 throw, I can only have k minus 1 different sides. Otherwise, I will have too many sides if I get a new side again. And then the number of ways you can get the new side, well, if k minus 1 sides are in the previous n minus 1 throw, then how many ways can I get a new side? S minus k minus 1. Because there are that many sides that you haven't seen in the first n minus 1 throw yet. And that's the first part. If the last throw, you get a new side. What if you repeat a side? Well, that means that the first n minus 1 throw, you already got k sides. And then the last throw, it must repeat one of the k sides. And that's it. That's the formula. Okay, so that's the recursive formula. And basically every time I want to compute f of n and k, I reduce n minus 1, I reduce n by 1, and I reduce k either not reducing it or reducing by 1. So as long as I know what the answer is for f of n equals to 1, then all of the things can be reduced to here eventually. Does that make sense?
Yes. So the first part of that formula is if you get a new side, and then the bottom part is repeating
When you
side.
repeat a side that you have seen in the last
Okay.
n minus 1 throws.
Yeah, that makes sense.
So then it's just a matter of computing. If this makes sense, it's just a matter of computing this. Now, instead of doing the number of ways, I can actually turn it into the probability. I can work that. I mean, before what I said was you can compute a number of ways and then divide by s to the n. But I can actually work it into here by turning all of this to be probability. So this would be 1 now. And then I just divide by s. And that would make it into probability already. And that's how I eventually implemented this. Wait, why does it? Nope. Okay, here we are. So I have basically this function f, which is computing the probability of n throws, I different sides, and s is actually doesn't change. S is the number of sides in my dice, and I just sum up all the possible ways of getting k k plus 1, k plus 2, all the way up to the minimum of n and s, because it doesn't make sense if k is bigger than s or k is bigger than n. And then the algorithm to compute this, probability of getting exactly k different numbers in n throws. Okay, so if k is equal to 0, so if I see no phases, or if k is greater than n, the probability is 0. So those are the edge cases. If n and k are both equal to 1, that's another edge case. And then this is the dynamic programming part. If I've seen this before, if I've already computed it, I just return it. Otherwise, the formula is exactly what I just showed you, right? So either it's a new, so this one is a duplicate. So I have to switch to the order of the two, but it's the same thing. So this is the duplicate, f of n minus 1k times k over s, or you get a new one. So f of n minus 1k minus 1 times s minus k plus 1 over s. I wrote s minus k minus 1, but k minus 1 was in brackets. So when you get rid of the bracket, it becomes k plus 1. And that's it. That's the algorithm. So again, I guess that what are the two things here? The first thing is we're trying to figure out how counting at least something, and it's quite often hard to count at least something. So the usual trick is to count exactly something and then sum up all the possible choices, provided that you don't have many choices. In this case, there are not that many because it's up to 500. So you can do this loop. And then once you decide to ask for exactly this many different phases, it becomes a little bit easier. And then the other moral of the story is to count things with recursion, right? So I look at the structure of the problem, I end those, think about what happens to the last one, try to figure out, what are all the possibilities. And in this case, I guess you can say there are only two possibilities. Either you get a new side or you don't. And then for each possibility, you figure out how the recursion goes and then add up the result. And that's a pretty standard way of doing the counting. So again, what am I trying to say? Unless what you're counting is something that's well known, like permutations, combinations, all those things that you learn in school and class, most of the time what you want to do is use recursion. You're gonna look at the process of generating the thing that you're trying to count. Throwing coins, throwing dice, you're gonna have a sequence of things, usually. When you have a sequence of choices, then typically you say, okay, what is the first or the last choice? And if you look at the possibilities of the last choice, can you then try to figure out recursively what the problem looks like with the previous n minus 1 choices? And then once you figure that out, then it's usually some kind of recurrence, and then you use some kind of dynamic programming to actually compute it. So I can't say that every single combinatorics or counting or probability problem is going to go this way, but most of them will be. Another thing is a lot of times probability and counting are really the same thing, right? Because to compute probability, you are usually counting the number of cases, the number of ways that you're interested in divided by the total number, right? So probability counting are very much related, and both of them quite often are solved by recursion and dynamic programming. So that's really, I guess, the theme of this past couple of weeks. Okay, I guess that's all I want to say for these problems. Any questions? So as usual, all of my solutions are available on my GitHub, right? So if you need to go back and refer to it, you can. Okay, for next week, do we have any requests for problems? Different types of problems? Anyone want to request anything? No. Okay. Oh, yes. Do you have a request?
Well, it's just well, yeah, I really liked the Fibonacci one because it was kind of uh, like I didn't know that the Fibonacci numbers could be used for that, and I had to figure that
Okay.
out. I thought it was cool
Okay,
because of that.
that's good.
So yes,
Um,
more problems that have cool math solutions because
okay,
I'm a
so,
math major.
okay. And now I think Jana, you also took quite a lot of math classes, right?
Yeah, fair amount.
And then Luke, I don't remember.
Yeah, I was a math major up until now. Now I'm a computer science major.
There's nothing wrong with that. I started out as a math major too, and then eventually kind of play a bit of both sides here and there.
Yeah. Yeah, it was just for my fourth year, it seemed like computer science had a lot more cool topics.
Okay, so in that case, I'm gonna choose something that's mathematical. I'm gonna choose for next week probably something to do with number theory. Okay, so these would be like things to do with products of numbers, prime numbers, and things of that sort. And maybe you've seen some of them, but maybe not in a computational way.
I've always wanted to try making my own computer program to produce prime numbers.
Okay, yeah, I can certainly show you how to do some of that. Yeah. So that's my plan then. Okay, so next week it will be number theory of various kind.
Sounds
Sounds
good.
good? Okay, let me